All right, welcome to SREcon. So yeah, this talk is an interesting balance. It's new content, certainly old problems. And I don't know if you've seen kind of those horrific action movies from the US. They all look the same, where people compare like bullet wounds with each other. These are all like production traumas. We have enough of them to fill up like a day's worth of content, but we'll try to keep it to ones that show like demonstrable takeaways, things that we actually learned. So a real quick context, what do we do? Circonus is a metrics and telemetry platform for monitoring. So we take in measurements of things. We make pictures out of that data, like graphs and heat maps and things like that. We do offline analytics, and we do stream-based analytics for millisecond level real-time alerting. So that sounds simple, of course, until you realize that billions of unique things are measured, and on each of those things, sometimes millions of measurements per second come in. So you can already see that that's like 10 to the 18th measurements per second sometimes that you can see in these systems. On top of that, things can disconnect for long periods of time because store and forward networks are challenging. And we run it as a SaaS, so it's multi-tenant. So now that simple, I take data and make pictures, turns into, oh my God, why did I take this job? What we just want to run through, we don't have too much time, is kind of 4 parts of the system that we designed wrong. And the things that we did to correct for those. And then we'll kind of sum up with some conclusions that might seem really obvious. There might be controversial statements as well, but there are things that we lose sight of as engineers because we're always trying to get better. We assume we won't make the same mistakes. That's not always true. So I'm going to dive right in. And this is sort of what our architecture looks like a little bit, except a lot of these nodes have 20 of them, or 2 of them, or 10 of them, or whatever. That's sort of what our architecture looks like today, more or less. So message queues. How many people here use message queues for something? All right. Okay, so our architecture, we started building it in 2010, before microservices were really a really popular thing. So our architecture is a little bit more macro service oriented. It's not like one API endpoint per binary running in a Kubernetes container, because Go didn't exist then, and Kubernetes didn't exist then, and containers, I would argue, still don't exist. But that wasn't really there. But we did componentize the architecture and have it communicate over the network, sometimes directly over things like REST, and other times over message queues. So typically in message queues, components learn of things through control messages. So a component will say, hey, I just changed this user. I created this user. So anybody who cares should probably do what they need to do about this. Or I just disabled this user. Or I just added this rule set or this collection point. And then the rest of the architecture subscribes to those events and learns about it and reacts. Well, the other thing that you might do over a message queue is say, I have this piece of data. I took this measurement. So what happens is that when you put 2 things over the same substrate, and one of them is very, very active, this happens, right? So if anybody's ever seen, anybody use RabbitMQ? Yeah, there we go. Anybody ever have it absolutely and utterly fail on you? So the problem that I have with RabbitMQ is only one, and it is that the pathology of its failure is incredibly hard to diagnose. So it works beautifully until it doesn't, and then when it doesn't work, it's incredibly difficult to understand why it isn't working and to triage. So in order to do this, what do? You do the same thing that everyone has ever done in every network ever, is that you separate your control plane and your data plane. So they're not labeled. Oh, they are labeled. Good. So the control plane, luckily, is not on fire anymore, right? So that the data plane, if we overload it, we'd start dropping or delaying data from devices and things like that, but the consistency and state of the system remains intact because the low volume queue around control can be isolated and the quality of service around that can be controlled. So it seems pretty obvious what you would do. The next step in this is to perhaps extinguish flames. In order to do that, we actually built our own message queue. And you would ask, why would you do that, of course? Why wouldn't you use Kafka? Because it's 2010, and Kafka didn't really exist. And I would say that the lessons learned here are that the things that you build in the past are almost always more optimized for your problem, and yet still a poorer choice for the things that you're doing today. So our message queue system works better than Kafka for our stuff. And if I was building it today, I would use Kafka. Right? It has a large community, it's stable, it's a benefit of open source. So FQ is also open source. Anybody want to join in and use our unpopular message queue, you're welcome to. It's fast, it's written in C. So 40 gigabit wire speed is not a problem on it. So it's kind of interesting, the movement from that message queue, and we moved into the cloud recently, and the idea of changing our architecture to use like cloud-based pub sub stuff was nuts, because we ran 2 FQ instances, and we were able to push around 1 million sustained messages per second through each one. Those messages are complex messages. They have hundreds, sometimes thousands of telemetry points in each message. So you're talking about millions, billions of telemetry points per second going through. And it costs somewhere between $15 and $25 a month to run that on our own hardware in a data center. And when you start looking at PubSub in like Google or Amazon, you're like, oh, that's like $80,000 a month. That's a little different than $15 a month. But it's important to know that all of these design decisions are based on available software and what's good enough at the time. And we'll get to that in a conclusion. So we replaced this, and now nothing's on fire. So it's kind of a one thing. So the horrible design decision here was, like, what idiot puts the data plane and the control plane on the same thing? Like this idiot does, right? Okay. So it's not, I'm not ashamed of that. There is a reason we did it. But what we did when we got out of that is we were able to track, we always track the latency of every message going through the system. Even if it's 1 million a second, we track every single one of them. So we were able to see when we did our deployment launch that we had all of our message latencies went down. Long tail went up a little bit, and the average went down. So you can see that entire shift down around that, which is fantastic. All right, so messages are flowing into the system. We need to store them. So we stored our messages in Postgres. So anybody here use Postgres? Yeah, almost everybody. That's great. I've been a part of the Postgres community for a very long time, and it's so encouraging to have hands go up more and more every conference. Postgres screwed us hard in this. I still love it very much. We still use it for parts of the system. But we basically turned Postgres into a column store, sort of the way Timescale DB, if you're familiar with that, sort of the way that works. The problem is that we weren't really pushing the boundaries of Postgres' storage model or query model. We were pushing the boundaries of its operational model. The idea of what happens when a node fails. And when you run a large enough system, nodes are always failing. And there is one truth in telemetry systems. Ingest never stops, ever. So if you're getting an average of 1 million per second and you have 5 minutes of downtime, it's not like the data just went away. I guess if you're some other vendor, you might be like, it's gone. But we can't do that, right? So like every mistake we make is memorialized forever in every user's graphs. Like if we have a 5-minute outage, it's 5 minutes missing in every graph for every customer. That would be crazy. So you can't do that, which means if you're down for 5 minutes, you have to catch up. So what we wanted to do was improve operational efficiency, improve storage efficiency. My clicker's not, oh, there it is. All right, so what did we do? We ended up defining our own storage format. So we used some genetic algorithms to design a structured layout for aggregate data. And then optimized it for LZ4 compression. We use LMDB-backed storage for that data. LMDB is like a memory-mapped database, embedded database. We use ZFS extensively. That's supposed to be LZ4, not LAZ4. And then what we end up with is it takes us about 8 bits for any given data point in the system. So you get an unsigned 64-bit integer, and we store that in about 8 bits, which is pretty good. So we also store histograms in the system. I'm not going to dive into the depths of histograms, but we've been storing histograms in the system for about 7 years now. Those graphs before, you can see all of the storage latencies, those are all histograms. So we decided to build our own database to do this, right? We wanted 0 points of failure. We wanted recovery and rebuild with no operational intervention. This was the key point there, is that when systems crashed, we had people busy. We had people toiling to bring systems back online, to make sure that users were unaffected by that. And just the mechanics of Postgres were very cumbersome to deal with. So we could try to either automate that or simply build a system that didn't suffer from those problems at all. So wait, stop, don't build a database. Why did you not just use InfluxDB or Cassandra or React or OpenTSDB? And again, it's 2010. Cassandra was a sort of okay choice for this, but it had some operational problems. And what we realized was that we had they all solved a problem that we did not have. So all of these databases, React and Cassandra, OpenTSDB not so much, Influx even, for I think no good reason, solves the consistency and coordination problem. They all implement like Paxos or Raft or something like that to try to agree. Well, it turns out when you're storing only telemetry data, you can make every operation commutative and idempotent. And in a distributed system, that means that you don't have to agree to be eventually consistent. I can get all of the messages in order or out of order or duplicated, and I still end up with the same ultimate answer. And because of that, we decided, hey, maybe we should write our own database that doesn't try to solve these other problems. And it turns out that it's really, really fast to do that. So at the end of that, what we were able to do is put nodes on different contents, completely different failure regions, completely uninterrupted ingest on failure. So you can have an entire data center fail, and you're still doing 1 million messages a second sustained inbound per node. And then uninterrupted analytics and read. So basically, our systems are failing all the time, and they're failing on purpose, right? We're actually deploying code and crashing them on purpose to understand their failure scenarios, because all of the engineers have complete confidence that it's not screwing any users, right? It doesn't affect the users. And that was the key. So sort of what it looks like is this. Looks like React or Cassandra, more or less. There are some subtleties and differences. Happy to discuss those if anybody wants to understand more about how that technique is done. So this is what our Postgres usage graph looked like when we first started the company. And this is what our Snoth usage graph looked like, which is now called IronDB. And this is the important part to see in that graph. That's 11 months of completely redundant bliss. In fact, when we decided in January of 2012 that we finally would make the switch over, we went in to change the code to do the switch over, and it was already switched over, and then we had to go back into commit logs to figure out when they had switched it over. Right? So we had actually been running on the new system for all default users and didn't know it. Right? So you could flip with an AB user flag to see which systems that you were using. All the data was going into both systems, and then the read was fanned out based on user cookie, basically. The idea that we could run all of these things all at the same time and flip back and forth between any of them at any time basically gave our engineers all of the security they needed to do to develop it faster and more confidently. And what do we get, because we're histogram junkies, is that we track the latency of everything in the system now. So we're able to track the latency of every disk I/O op. We're able to track the latency of every put call in the database, get call, REST endpoints. Every single thing is traced in the system. So this uses the open source statistics library libcirclehist. It's a C stats framework called libcircmetrics. Both of them are like BSD licensed. So we can track all of this, and there's a 9 nanosecond flat recording fee for tracking any of this. So it costs more on most systems to figure out how long it took than it does to remember how long it took, which is really cool. And then the other thing that we got for free is we got distributed tracing. Oops, I'm gonna go back one. We ended up kind of getting addicted to Zipkin, which was the older version of open tracing. We built into our kind of C library framework, which is called libmtev, which is also open source. We built all of the statistics stuff in. We built distributed tracing. So every time you build an app, you get complete distributed tracing. And one of the cool things, because we're all systems level junkies, is that we consider the application itself a distributed system. So the 100 threads that are in there where you're handing from one event pool to do asynchronous I/O to another one, all of those are distributed components. We can see the traces between each callback function and migration between threads. We can see every single one of those steps. So when I light up a single GET call that pulls back, say, I don't know, 10,000 data points, I can have 4,000 or 5,000 of these traces and see every single inner working of the system. It's not just big macro component to other macro component. It goes from thread to thread. It's incredibly useful for debugging, like, why did I have an extra millisecond of latency here, right? So when I pull data out of a system and do, say I want a year's worth of data, I expect that to come back in a millisecond or two. So this one came back in 0.77 milliseconds. We're all good. When it doesn't, finding those little tiny bits, it can be really, really difficult. So we'll get to what was important and learned at the end about all of this stuff. I'm going to hand it over to Heinrich.
Thank you. Yeah, by the time you might have wondered, what is this guy doing here all the time? So I'm Heinrich. I work for Circonus as well. This guy hired me like in 2014 to take care of the analytics tooling that we have. I have a background as a mathematician, but as I will tell you in the next slides, I also ended up doing mainly coding for the last few years. So when I started, it was not in 2010, it was a few years later, but the basic architecture back then looked like this. Theo already had that component on his slide. I organized them a little bit more nicely and put a bit more errors between them. So basically, we have a bunch of brokers, which are like agents you run on your boxes, but they have a more hybrid characteristic in that they can also run their own checks. But data comes from the brokers. It's then ingested by a component called SREcon. And then what we had from the very beginning in our architecture was a branched out data path here. So our alerting path runs through this FQ message queue and then is put to an alerting system that sends out messages. And the storage path was always different. We ingest things to Snowth, or now it's called IronDB, and then we have WebUI, which feeds from there. So, and today I'm gonna talk about stream analytics. So if you look here, we're in the upper part of this diagram. We also have some analytics in the lower part, but I only have so much time, so we are going to do this story here. So the feature request that started that was that people started to want to alert on analytics transformations or on more things than just thresholds. The first thing was like a forecast. So you're forecasting your disk space, and you're going to be notified if you're running out of disk space in like 3 days or something. And that depends on the value and also on the velocity of your ingest. Also, we have these native histograms. They are great, but you need to actually transform them into numeric values to be able to alert on them. So histogram percentiles were another thing. Then we had a query language, and we want to give users the possibility to alert on queries. That's also natural. And then we had some crazy plans just to do transformations on all metrics and just like automatically find out if something goes wonky. So this was somehow the stuff we wanted to achieve. And the first idea, like what many people do for analytics alerting, is just to poll the database. Database is already smart, has some stored procedures which can do the computation, and you just poll it. It works. It's pretty simple. The problem that we initially had, we kind of solved part of that more recently, is that the data in IronDB was a little bit delayed behind the queue. So in the alerting pathway, we had like millisecond latencies between the samples hit and we can act on them. In IronDB, you have to first like get it on the database, replicate it in the database, and then when you hit one node, you're sure to be able to pull it out. So it was like 30 seconds, maybe a minute. So it was delayed. More recently, this has gone down to the low digits in seconds, but by the time there was a significant gap. And the thing that always struck me as very unfortunate was that you were actually putting a constant load on your database in this way. So if I have 10,000 alerts on stuff, I'm doing 10,000 requests like every single minute. So it's like, okay, and actually the results of them look very, very similar. You're pulling like 3 months of data to compute your analytics transformation, and you throw all of it away and just look at the very last data point. And then 1 minute later, when your window just shifted by 1, you're almost doing exactly the same computation again and just querying all the data again. And of course, it completely breaks down if you want to do alerting on all metrics, because it means that now all your data for the last weeks has to be hot in your database, which is just very expensive to do. So we thought we will be better. We build a stream analytics component. That's always a fun thing to do. And by the time we wanted to be minimally invasive in the architecture, so we just said, well, I can stick it into FQ, just have it listen to all messages, spit out messages again, and then we will have analytics transformations. So we avoid the load in IronDB this way, and we can reuse our existing code we have on the database. It's in Lua, so the component was using C++ and Lua JIT by the time. And so the thing we wanted to achieve, it worked. It was okay. So this is latency profile of our current our database. So typical analytics queries took around 270 milliseconds there, which is, it's okay. I mean, if you're doing just the simple queries I talked about, you might be able to get that down to 50 or 20. That should be maybe possible, but this is the update performance of the speaker system. And that's actually a log axis, and here is the 10 microsecond tick. So we are roughly a factor of 1,000 faster by processing messages this way. And it shouldn't be too much of a surprise. We are not doing much I/O. We're just reading in the message, and then we have some state in memory and updating that state. So it's just a bunch of load operations. So this is naturally very fast. This was great, but actually we had quite a lot of regrets when we were a good year in and had the first prototype of that ready, which ultimately led to us redoing the whole thing. So the first lesson that we learned the hard way was that minimal changes to the architecture don't mean minimal changes to the product. So this was really easy to build and integrate into the service, but it meant that we had to introduce new concept in our system. So we now had an analytics transformation that you can apply to an existing metric, and you could alert on transformations, and we needed a lot of UI work and conceptual education of our users to be able to make use of that. So it costs us a lot to do it this way. The second thing is, if you go back to this slide, you see that the results of the analytics transformation are just not being persisted. They just go through alerting or not. So if an alert was sent out, the user will not have history of that transform in order to make sense. Did we screw up? Was it a legit alert? What's actually going on? In particular with stuff like an anomaly detection, which is very fuzzy, you want to have some history to see when did it actually take over. So we didn't have that with that architecture. And the third lesson, which might be most relevant to this audience, is that we drastically underestimated the operations tooling we needed to build to actually make that work. So just for example, we have a service called Backtrace, which takes care of postmortem debugging. So as soon as someone blows up, that has to it goes to the cloud. It's not terribly hard to set up, but maybe half a day of work. Then there is logs, configuration, instrumentation, tons of things, packaging. At CI, a lot of things that you just have to do. And it took a significant part of our whole development effort to build all that tooling, because also the uptime requirements are pretty high for this. It's in the alerting path. You just want it to run. And finally, also interesting, we saw a critical requirement for that service. As soon as we build it, that users will come to us, well, can I actually aggregate metrics with it? Can I build a sum of 50 metrics, or can I merge my histograms together? We were actually, no. We oversaw that. So it's not terrible, but the concept of a transformation that I talked about earlier was just tied to a single metric. A forecast is always based on a single metric, so we're yeah, we should change that. And it's not terribly hard to change it, but we were already a good year in and trying to get it out, and we just realized it's not good. And Yeah, so I thought about that when I was through everything, and again, how did it come that we just made that bad architecture choices? And so it's on this slide. So actually, in 2015, when this effort was undertaken, we were under a situation that we have a new CEO. Theo was taking a sabbatical back then, and the new CEO come from sales, and he was super excited about this whole thing. He was like, okay, when can I sell this? This is awesome. We had a new CTO come in, and he came from the operations kind of things, and he was very focused on the stability of the system. And he was like, okay, you can do whatever you want, but just don't break it. And we had a new team. I mean, I was onboarded, and we hired a guy from Mainz and some other people to work on that, but it was a completely new team. And the first question we all had was like, what is OmniOS? You might also have that question. You can look it up what it is, but it's a lot of fun. Well, okay, but the situation changed. Like 2016, Theo came back, he assumed back the role of CEO, and he said, well, yeah, that's not good. I think we need to redo that. And we said, well, yeah, actually, it's not pretty. We hit a wall there. Maybe it's worthwhile to put that in the trash bin. And we had a new CTO come in, and this guy was really amazing. His name is Riley Burton. And I've never seen a guy just grogging so much code in so little time. So he was there for 2 weeks, and he basically just read through all the code. I mean, this is stuff that took me like really months and months to wrap my head around, and he was like, okay, I'll check, I know how this works. And actually, why did you just reuse our existing technology? Like, we have a thing which roughly looks similar, the broker at the very beginning. Why don't we use this? And that's actually a pretty smart idea. We had kind of thought about using existing technology which lies below. So we have a library called AMTEF, which is a multi-threaded server framework, which we use everywhere. It's also open source. But we were not able to get on our feet with the new team just reusing that tech due to the situation back in the day. So, but now, like 2016, Theo was back there, Riley was there. We had enough people, and it was a good insight to be able to reuse that technology. And it turned out to work quite well. And the redo of the whole thing didn't take very long. We moved a lot of the logic from C to Lua, which is a little bit more dynamic. We could do that effort quite fast. And also, since we already had build up all the code in C++ before, we know what we were doing. So it didn't really take that long to re-architect it. And now this is how the architecture looks. And I don't know if it looks more pretty, but it does make a lot more sense. Because now the output of CAQL broker are just metrics. So every transformation is just another metric. I don't need to change the UI for that. We already know how to do metrics. So it's just another metric. You can threshold it. It's very beautiful. Minimal changes to the product. A little more changes to the architecture because you have a new broker. So, yeah. What do I have a pros? Existing code base? Yeah. And the great thing really is we can reuse our ops tooling here, and that's pretty huge. Because I told you how much pain it was to build it. Now we already have a broker which was there from the very beginning and had all these great tools around it. So we were just be able to use it. And with this component in particular, like observability of this thing is absolute key to operate it. It's a thing that accumulates state over time. We have a standing query which sits there over weeks, and it's stateful. It takes updates from messages. So you cannot just restart that and deploy new code. I mean, you can, but you will destroy all the state, and then you will have not the pathological behavior that you had before. And also, if you try to reproduce stuff in depth, you need to replay a lot of data before you arrive in a state that has these defects. So it's very critical that you understand the system while it's running, and you're not changing it and doing any harm to it. And it keeps running while you're doing the debugging. So, and for me, at least, what I make out of this term, this is really the key aspect of observability, that you can understand the running system and not do harm to it. So what we do is we have pretty extensive logs. So everything it does, it just goes to the disk first. We can still sustain that. Well, as log message, and we can tune the granularity of what we need. We have a lot of instrumentation. Read and use methodologies for the endpoints. And we always have a stats.json which spits out JavaScript of a lot of just statistics which are in there. And we have introspection capabilities via Telnet and web, and I have some pictures of this. This is beautiful. Oh, here's it. So that's something we just inherited from the broker. It always had a nice web inspection front end, and we can just like put the stuff we were interested in on here. And it's, yeah, I like it a lot. Some people prefer Telnet or different things, but it's nice if you have a nice UI to look into that. I will also quickly show you the metrics, how it looks like. This is a small example system that we run. I like to put in the first row the service level metrics. So we have an uptime metric here, which is critical, number of checks we're running, messages in, messages out. And then this is a 2-node cluster. So it's the right side and left side, 4% CPU. And we use like kind of a use methodology for metrics. So it's utilization and then saturation and errors are in this chart. So we know not only if it's fully utilized, but also if it's saturated, if I have a bottleneck there. So that's very, very happy. That's actually not so happy, so it tells me in 17 hours I'm out of memory, so it will reboot. Yeah, it's how things are sometimes. Yeah, this is self-monitoring. That's a little fun because we are actually emitting metrics. So to test it, we just graph the metrics, and if everything, these are the transforms that are computed. For example, here 1 + 1 is 2. We compute that every minute and make sure it's still 2. And then we do outlier detection and all the analytic stuff as well. And if it's smooth, then it's smooth. Right, so this is what I currently use for log analytics. It's not pretty, but it kind of works. So you just rsync the logs over, make a SQL database out of it, and then you can actually run select queries against it. So it's a very poor version of ELK or Splunk, but it's good enough for me right now. And you have this little tool called feedNewPlot, which allows you to produce histograms like the one I had on this slide. So that's feedNewPlot. Yeah, of course. I don't know what's the bottleneck here. OK, great. Check inspection. Yeah, and the one last thing I wanted to touch on was high availability. So that was something that landed quite late. We didn't have it in Beaker, which was a pain. And in the broker tag, we had kind of halfway done high availability setup. And Theo went in, he spent half a day, and he just like finished coding. And then I took half a week and finished testing. And then we got that high availability or like the clustering. Like it took a while to get it out of the door, but the principal idea is quite simple. So you run a bunch of CAQL brokers, and then they communicate via heartbeats, and they tell each other how long they have been up. And if you see a node that is longer up than you are, then chances are that the state of it is going to be better than yours. So you just mute yourself and say like, somebody else is taking care of that. So it's pretty simple. We don't do federation of the messages yet, but it has not bitten us because the system is just quite effective. We can run it at a scale that we need at the moment. Right. So yeah, this is how it works. And we have some logic to replicate checks. So if you add a check to one of those brokers, it gets replicated. So once we had that out of the door, it was like I didn't realize how big of a feature that was. We didn't have a lot of downtime before. So I thought, OK, great, then we do not longer have any downtime. But the operability of the service improved by just an order of magnitude. I was way happier when we done that, because every deployment of CAQL Broker was super stressful for us. We emit metrics which are persisted, so every minute we lose is visible on our graphs. And every deployment back in the day meant at least one sample that we were missing, because it takes some time to start it back up. And so if something goes wrong, you're looking at least at a 5-minute outage until you have rolled back everything, and maybe even longer than this. And then you're in a situation, OK, you have rolled back your deploy, but you cannot reproduce the error you were seeing. So fingers crossed your logs are good enough or the telemetry you were emitting there. But often it was not. So we were like, OK, just going to change something and redeploy it, and you have another outage. So it's not great. With high availability, you can get away with stuff like that. So in black, it's the service uptime, which is always the uptime of the longer running node. And below in blue and green is the individual node uptimes. So I can get away with like doing a deploy and finding out, nah, it's not good, code change, redeploy, code change, and the user doesn't notice anything. So it's really like, I can get away with like a lot of errors that I only find in production, and I can debug it while it's there with the real data. And if I'm, like, the only thing I have to make sure is that the other node is still working. And it's usually up for a few days, so that's fine. So yeah, this was like a little revelation for me, so I thought I'd share that story. And a little tiny takeaway, if you want to save on CPU, it's a good idea to not run garbage collection all the time. So literally all the time. This is a line of code that was hit like hundreds and hundreds of times each second. And I was always thinking, why is my component doing so much garbage collection? I'm really, really bad at producing objects. No, we're just really, really good at calling garbage collection. So something to keep in mind. Right. So, and this is our architecture, how it looks right now. We have this CAQL broker, which is sitting there quite happy. We have IronDB, which had Lua extensions for a while, and CAQL as well. CAQL is our query language. One nice thing about this is that we are able to run the same queries on our CAQL broker and on our database. So it's one language you have to learn. You get standing queries, and you get offline analytics, which is also a challenge of its own, but that is a different story. And with this, I give it back to Theo.
So yeah, that GC problem was interesting. It always feels good when you go in and make one surgical line of code change and you get like 90% reduction in utilization, and then you realize you're the one who put the original code change in that caused the problem. It's really sad. How many people have put debugging lines that you didn't intend to put and committed them in? Right, everyone has slipped. That was effectively what that was, is we had this weird problem where things were we were getting these crashes, and it was because we had an inversion on usage, and it was a use after free problem. We were GCing and still using it. The best way to test that is to force a full GC so that your use after free happens sooner. And the next part of that is to not commit it for perpetuity in production, which was the accident. So I think the important takeaways here, because I imagine our architecture doesn't really apply too much to everyone else's architecture, is that I wrote a book on scalability, right? So Internet Scalable Architectures is mine. I've contributed to a whole bunch of other books. In the past, before Circonus, I got paid ridiculous amounts of money to go in and help people solve large-scale production problems, data flow problems, performance, scalability, all of that. And the vast majority of the mistakes, because I started Circonus, are mine, right? So you're going to make mistakes. The interesting part is that I've often said, you know, making a mistake is fine. Making the same mistake twice is kind of stupid. I've made the same mistake more than twice, over and over and over again. I mean, like, who the hell conflates the data plane and the control plane? I mean, like, when early on in my career, I was like, you get to make that mistake once or twice. Well, the truth is that no one ever thinks of real-world scenarios constraining your development and your design paradigms. And that real-world constraint is time to market. Like, you have to get the feature out. It's always funny, people are like, well, we just can't control how long it takes. And it's like, I can control how much money we have left in the bank. So that's how often you get paid. So it's going to get released, or you're not going to have a salary. Like, this is real. You have to release these things. And those mistakes tend to be mistakes you've made before, and it's for one reason, is because that's the technical debt you understand the interest rate on. Like, I've made that mistake before. I know how much it hurt. I can tolerate that much more pain in the future when it bites me, and I can fix it then. That time I can get back later. And I think that those are really good technical debt decisions. Once you've been served your collection notice on your technical debt, this is a controversial statement, and I'm sure it'll be taken out of context at some point and make me look stupid, but focus on operability over correctness, right? You're not going to get either one of them right. That's the reason. It's not going to be operable, and it's going to be broken. The best case scenario is that it's at least operable enough for you to understand why it's broken, right? So you have to be able to run this stuff in production. Instrumenting systems, if you don't instrument them, you have no idea what's going on, and there is no way to win. You absolutely have to be able to understand what your systems are doing in production and how they are behaving, and you need to know that in the past as well. You need history around this stuff. And then the last one, which is the most probably obvious and least objectionable, but perhaps the hardest to do, is that if you don't build your systems resilient and redundant enough, your development, your software engineering practices, even your SRE practices, will be paralyzed because you will be afraid to make changes. So build it safe. And that's it.